Top 20 Hardware Engineer Interview Questions and Answers. Are you preparing for a hardware engineer interview and want to stand out from the competition? In this video, we've compiled the top 20 most commonly asked hardware engineering interview questions along with detailed, expert-approved answers. Whether you're a fresher or an experienced candidate, this guide covers technical concepts, tools, troubleshooting methods, and real-world scenarios to help you confidently tackle any interview. Let's dive in and boost your chances of success. 1. What are the basic components of a computer system? A computer system consists of several fundamental components that work together to perform computing tasks. The central processing unit, CPU, is the brain of the system and handles instruction execution. Memory units like RAM provide temporary storage for running programs, while RAM stores permanent instructions. Input devices, for example, keyboard, mouse, allow user interaction, and output devices, for example, monitor, printer, display results. The motherboard connects all components and provides data pathways. Storage devices like HDDs and SSDs are used for long-term data storage. Power supply units convert AC to DC power to run internal circuits. Additionally, graphics cards and network interface cards enhance visual processing and connectivity, respectively. These elements together define a functional computer system. 2. Can you explain the difference between RAM and ROM? RAM, random access memory, and ROM, read-only memory, serve different purposes in a computer. RAM is a volatile memory used for temporarily storing data that is actively being used or processed by the CPU. Once the power is turned off, all data in RAM is lost. It plays a crucial role in system speed and multitasking capability. ROM, on the other hand, is non-volatile memory that permanently stores critical system instructions, such as the BIOS or firmware. These instructions are necessary for system startup and do not change during normal operation. Unlike RAM retains its data even after the power is turned off, making it essential for system boot and hardware initialization processes. 3. What is the function of a motherboard in a computer system? The motherboard is the main printed circuit board, PCB, in a computer that acts as the central communication backbone. It connects all the key components of a computer system, including the CPU, RAM, storage devices, GPU, and input-output ports. It provides data pathways, buses, for communication between components and houses essential chipsets that manage data flow and control interfaces. It also contains BIOS/UEFI firmware for booting and system configuration. The motherboard includes power connectors, expansion slots, PCIe, and SATA or M.2 connectors for additional devices. In essence, the motherboard provides both physical structure and logical communication to ensure all computer components operate cohesively and efficiently. 4. What are buses in computer architecture? In computer architecture, a bus is a communication system that transfers data between components of a computer or between different computers. It acts like a highway, enabling data to flow between the CPU, memory, input-output devices, and storage units. There are 3 main types of buses: the data bus, which carries actual data, the address bus, which carries information about where data should go, and the control bus, which carries control signals from the CPU to other components. Buses can be parallel, multiple bits transmitted simultaneously, or serial, data transmitted bit by bit. Modern systems often use high-speed serial buses like PCIe and USB to improve data transfer efficiency and reduce latency. 5. What is the difference between microprocessor and microcontroller? A microprocessor is a general-purpose processor that performs computing tasks using an external memory and I/O interface. It is commonly used in PCs and laptops. A microcontroller, on the other hand, is a compact integrated circuit that includes a processor core, memory, and input-output peripherals all on one chip. Microcontrollers are designed for specific control applications such as embedded systems, IoT devices, and automotive electronics, while microprocessors offer higher processing power and are suitable for multitasking environments. Microcontrollers are optimized for low power consumption and real-time operations. 6. Explain the working of CMOS and TTL logic families. CMOS, complementary metal oxide semiconductor, and TTL, transistor-transistor logic, are two types of logic families used in digital circuits. CMOS uses both NMOS and PMOS transistors, resulting in very low static power consumption, as current flows only during switching. CMOS technology is used in most modern ICs due to its high noise immunity and density. TTL, on the other hand, is based on bipolar junction transistors and consumes more power even when idle. However, TTL circuits typically have faster switching speeds than early CMOS but are now largely replaced due to CMOS improvements. The choice between them depends on the application requirements such as speed, power consumption, and noise tolerance. 7. What tools do you use for hardware design and testing? Hardware engineers rely on a variety of design and testing tools to create and validate circuits. For schematic and PCB design, tools like Altium Designer, Eagle, KiCad, and OrCAD are commonly used. For simulation, software such as AltSpice, PSpice, and Multisim helps model and analyze analog and digital circuits. When testing physical hardware, engineers use oscilloscopes, multimeters, logic analyzers, and signal generators to measure voltage, current, timing, and signal integrity. For firmware development, Keil, MPLAB, and Arduino IDE are frequently used depending on the microcontroller. JTAG debuggers and in-circuit emulators help with debugging and troubleshooting embedded systems. These tools ensure the reliability, efficiency, and safety of hardware products. 8. What is FPGA and how is it used in hardware engineering? An FPGA, Field Programmable Gate Array, is an integrated circuit that can be configured by the user after manufacturing to perform custom logic functions. Unlike fixed function ICs, FPGAs are reprogrammable and consist of logic blocks, interconnects, and I/O blocks that can be wired as needed using hardware description languages like VHDL or Verilog. FPGAs are used in applications where flexibility, high-speed processing, and parallelism are required, such as in digital signal processing, data centers, aerospace, and automotive systems. They allow rapid prototyping of complex logic without fabricating custom silicon, making them essential for testing new architectures before committing to ASIC designs. 9. What are the common causes of hardware failure and how do you troubleshoot them? Common causes of hardware failure include overheating, electrical surges, component aging, manufacturing defects, physical damage, and poor ventilation. Environmental factors like dust or humidity can also degrade performance. To troubleshoot, the first step is isolation. Identify whether the issue is with the power supply, memory, CPU, or peripheral components. Use diagnostic tools like multimeters, oscilloscopes, or power-on self-test results to detect faults. Swapping components, for example, RAM modules, with known good ones can help. Thermal cameras or temperature sensors detect overheating issues. If firmware or drivers are involved, updating or reflashing them may solve the problem. Documenting symptoms and testing step-by-step ensures accurate diagnosis and effective hardware repair or replacement. 10. Describe your experience with PCB, printed circuit board, design. PCB design involves converting an electronic circuit into a manufacturable board layout. My experience includes using tools like Altium Designer, KiCad, and Eagle to design multi-layer PCBs for embedded systems and sensor interfaces. I begin with schematic capture, defining components and connections, then move to board layout, where I optimize trace routing for signal integrity and minimize EMI. I follow DFM, Design for Manufacturing, guidelines, considering trace widths, clearances, and thermal reliefs. I've also worked on Gerber file generation, BOM, Bill of Materials, preparation, and design rule checks, DRC. During prototyping, I collaborate with fabrication vendors and perform functional and electrical testing to validate the design before production. 11. How do you ensure signal integrity in high-speed digital designs? Ensuring signal integrity is vital in high-speed digital design to prevent data corruption and timing issues. I apply techniques such as controlled impedance routing, short trace lengths, and matched trace lengths for differential pairs like USB or HDMI. I also use ground planes to minimize inductive noise and decoupling capacitors near power pins to reduce voltage fluctuations. Termination resistors help in minimizing reflections, while proper PCB layer stacking reduces crosstalk. Simulation tools like hyperlinks or SEWave are used during the design phase to analyze and validate signal behavior. I also maintain rise/fall time control and avoid stubs or sharp angles in routing. Testing is performed using oscilloscopes and time domain reflectometers. TDR. 12. What is EMI/EMC and how do you minimize its effects in circuit design? EMI, electromagnetic interference, refers to unwanted electromagnetic signals that can disrupt the performance of nearby electronic devices. EMC, electromagnetic compatibility, is the ability of a device to function properly in its environment without emitting unacceptable levels of EMI. To minimize EMI/EMC issues, I follow practices such as using ground planes, shielded cables, and ferrite beads to block noise. I keep high-speed signal traces short, avoid loops, and use differential signaling where applicable. I also place decoupling capacitors near power pins and ensure proper PCB layout, such as separating analog and digital grounds. During testing, I use EMI chambers and spectrum analyzers to ensure compliance with regulatory standards like FCC or CE. 13. Have you worked with any simulation software like SPICE or Multisim? Explain. Yes, I have experience using SPICE, simulation program with integrated circuit emphasis, and Multisim for simulating electronic circuits. These tools allow me to model analog and digital behavior before physical prototyping. I use SPICE for analyzing transient response, frequency behavior, and DC operating points of circuits such as amplifiers, filters, and power regulators. In Multisim, I appreciate the user-friendly interface for breadboarding and mixed signal simulation, which is great for rapid prototyping and educational purposes. Simulation helps in identifying component stress, power consumption, and signal behavior, allowing me to optimize designs and reduce iterations. I often validate simulation results with real-world testing to ensure accuracy and reliability. 14. What are the different types of memory used in hardware design? Memory in hardware design is categorized based on function and volatility. Volatile memory, like RAM, random access memory, stores temporary data and is erased when power is lost. RAM includes SRAM, static RAM, for fast cache memory, and DRAM, dynamic RAM, for main memory. Non-volatile memory, such as ROM, read-only memory, flash, and EEPROM, retains data even when powered off. ROM is used for firmware storage, while flash is common in SSDs and embedded systems. Cache memory sits close to the CPU and speeds up data access. In embedded systems, FRAM and NVRAM are also used for specific low-power, high-endurance applications. Selecting the right type depends on speed, size, power, and permanence requirements. 15. Explain the concept of clock synchronization in digital circuits. Clock synchronization ensures all parts of a digital circuit operate in harmony, using a common timing signal known as the clock. Every flip-flop or sequential element in a system responds to clock edges, rising or falling, making timing predictable and reliable. In complex systems, clock skew, difference in arrival times of clock signals, can lead to errors. To manage this, engineers use clock distribution networks, phase-locked loops, PLLs, and delay-locked loops, DLLs, to align clocks across components. In systems with multiple clock domains, clock domain crossing, CDC, techniques like synchronizers or FIFOs ensure safe data transfer. Accurate clock synchronization is essential for avoiding setup and hold time violations in digital logic. 16. How do you optimize power consumption in hardware systems? Power optimization is crucial, especially in battery-operated and portable devices. I apply multiple techniques to reduce power consumption. At the circuit level, I choose low-power components, use efficient voltage regulators, and implement power gating to shut down unused modules. At the design level, I employ clock gating to disable inactive circuits and dynamic voltage and frequency scaling, DVFS, to adjust power based on workload. I design for low quiescent current and select low dropout, LDO, regulators where efficiency matters. On the PCB, I ensure tight power routing, short traces, and effective thermal management. I also use simulation tools to analyze power consumption under different operating conditions before hardware prototyping. 17. Describe a hardware project you've worked on from design to implementation. One significant project I led was the design of a custom embedded controller for a smart sensor system. I started with requirement analysis, selecting a low-power ARM microcontroller and relevant peripherals like ADCs and communication interfaces. Using Altium, I designed the schematic and PCB layout, ensuring proper grounding, signal integrity, and component placement. I simulated analog circuits in LTSpice, then fabricated and assembled the prototype. I developed firmware in Kiel, tested the system using oscilloscopes and logic analyzers, and debugged using JTAG tools. After thorough validation, I collaborated with vendors for mass production and created documentation for support and maintenance. The system is now successfully deployed in an industrial environment. 18. How do you keep up with the latest advancements in hardware technology? To stay updated, I regularly follow industry publications such as IEE Spectrum, EDN, and Embedded.com. I also attend webinars, conferences, and trade shows like CES and Embedded World, where I learn about emerging technologies and tools. I subscribe to forums and newsletters from vendors like Texas Instruments, Analog Devices, and ARM. Online platforms like YouTube, GitHub, and Stack Overflow help me explore hands-on projects and code examples. I take online courses on platforms like Coursera and edX to enhance my knowledge in areas such as FPGA design, embedded systems, and hardware security. Continuous learning ensures I stay competitive and innovative in hardware engineering. 19. Explain how you test and validate a new hardware prototype. Testing and validation are critical to ensuring a prototype works as intended. I start by verifying the power supply levels and signal lines using a multimeter and oscilloscope to ensure the board is safe to power up. I perform continuity and short-circuit checks, then move to functional testing by programming the firmware and observing system behavior. Using logic analyzers, I verify digital signals and timing, while spectrum analyzers help with RF components. I test communication protocols like I2C, SPI, UART, and check sensor outputs. I document all test results, identify any anomalies, and iterate on the design if necessary before moving to mass production. 20. How do you collaborate with software engineers during product development? Collaboration between hardware and software engineers is essential for successful product development. I begin by aligning on system architecture, identifying which functions are handled by hardware versus software. We use shared documentation platforms like Confluence or GitHub to maintain specs, pin mappings, and protocols. I provide the software team with detailed interface definitions, timing diagrams, and firmware hooks. During integration, we conduct joint testing sessions to verify functionality and resolve bugs. I also assist with hardware abstraction layers, HAL, and provide debug tools for firmware development. Effective communication, version control, and synchronized milestones ensure smooth co-development and a reliable, well-integrated final product. Thanks for watching our top 20 hardware engineer interview questions and answers. We hope this guide helped you understand key topics and prepare effectively for your next interview. If you found this content useful, don't forget to like, share, and subscribe for more tech career tips and interview preparation guides. Stay tuned, stay sharp, and good luck on your journey to becoming a top-tier hardware engineer.